Hello and welcome to the last lesson in Unit 4. And the last topic we're going to look at is Bernoulli's principle. So the learning goal for today, I want you to be able to tell me what Bernoulli's principle is, and then tell me some of the applications that exist out there. So some of the transportation and sports technology that exists. So what is Bernoulli's principle? There's a definition for you. You want to be able to identify it on a test, but Bernoulli's principle is this: where the speed of a fluid is low, pressure is high. Okay? So if the speed is low, our pressure is high. If the speed of a fluid is high, the pressure is low. Okay? So they are opposite. Speed. So let's do it like this. Fluid speed and pressure are opposite. To help remember. All right, keep it simple. So, example I have here for you. Here is a pipe system. So what we have is a large diameter pipe. So if you're pumping water into this pipe, because there is a large diameter, D1 versus D2, so D1 is much bigger than D2, what will happen is that we have a slow water flow through that pipe. All right, you would need a larger pump if you want to speed it up. Regardless, what happens is then all of this water has to fit through that pipe there. So the only way for flow to maintain or have a steady flow rate, okay, so you have the same amount of water going through the system, is that the water is going to have to travel much faster in this section to get through. So then the water then will spread out, allowing it to slow down again. Okay? So that means that if we have slow-moving water, and I just arbitrarily say this is the pressure level, so this is our pressure indicators. Pressure indicators. All right, these tubes sticking up. All right, so the water in this section, this is the pressure. It's under that much pressure. It will be, if this diameter is the same on this side, this is also a D1, the pressure will be the exact same. All right. In that faster region, based on Bernoulli's principle, pressure is going to be much, much lower. All right. So this is my direction of flow. That's to the right, as indicated by all the arrows in there. Direction of flow. So the pressure underneath, I've got a note here, the pressure in a pipe depends on two things: diameter and speed of water. Okay, so that's what pressure depends on. If you want to increase your pressure, you need to, depends on what you're going here for, but if you think of a garden hose, okay, you can increase the speed of your water by covering up the end of the garden hose. So if you're holding your garden hose, all right, so this is supposed to be my garden hose opening. If you just leave it like that, the water flows out like that. However, if you put your thumb on it, the water will shoot farther because you've increased the velocity by making the opening narrow. So just put that underneath. Think of a water hose. Okay. Narrow opening. And I'll put thumb on the end. Increases water velocity. And shoots farther. All right, and think of that stream. When you have your thumb on it, all right, it's kind of a misty water spray. That's because it's a lower pressure. So even though you're spraying farther, the person that you're spraying at isn't receiving all the water because of the lower pressure. The water's kind of dissipating as it travels through the air. All right. So, talking about some examples here. So looking at, first of all, the paint sprayer. So the paint sprayer has an air source, all right, under pressure. So what happens then is at this point here, we have reduced pressure. Reduced pressure, or I guess you can call it kind of a semi-vacuum. And what that semi-vacuum does is, like the straw we talked about earlier, it sucks, that vacuum causes your paint particles to come out of the can and spray with that air spray. So it comes out at a high speed, that air spray. However, what's happening is the air flowing over top of the hole in the can there reduces the pressure, causing a semi-vacuum. So I'll just put air causes, I guess I don't have to say semi-vacuum, it causes a vacuum to some extent. Paint is, and I'll put it in quotes here, sucked up. And this is similar to a straw. Similar to drinking a straw. And just instead of sucking, we're blowing to cause that pressure difference, similar to drinking a straw. Okay? The next is the airplane wing. So the airplane wing, what's happening with it? Well, we have air approaching the wing. So I'll draw it like this. What happens is that some of the air strikes the wing and gets deflected a little bit, but it really, we'll call it, to simplify, fairly undisturbed as it goes underneath. Now, the air that goes over the wing is compressed together, but it also has to go farther. So, has to travel, air has to travel farther. So if the air doesn't want to move based on Newton's first principle, because the air, we'll call it stationary, the plane's going through the air, that means that we have an increase in velocity. So air travels faster over top of wing. All right, so if the air is traveling faster, that means that we have a low pressure here, we have a higher pressure there. Because that low pressure exists above the wing, we have an uplift force. So it all is on the design of that wing, causing that air to be faster going over the top and decreasing the pressure. So pressure over wing, is decreased. High pressure underneath. Causes your lift. All right. And the car spoiler is simply just an airplane wing upside down. So what happens is we have, again, I've got my air approaching our spoiler. The air that goes underneath is going to have a higher velocity because it has a longer distance. The air over top, relatively undisturbed. So because we have a high velocity down here, here's my low pressure, here's my high pressure, and what a spoiler does is it helps keep the car on the ground or increases the force on the wheels, which allows for less or more friction, which allows for less spinning and so forth. So we have our instead of an uplift, we have our downforce. And that downforce increases traction, I guess. We'll keep it simplified. So we have a construction example with how the paint sprayer works, aerodynamics, fluid dynamics is very important in the airplane wing, and the car spoiler, also the same when we're talking about automotive technology. Now at the bottom, what I want to show and talk about is the physics of the curveball for the athletes here, and every sport has its own aerodynamics or fluid dynamics. There was a big controversy with the shape of the soccer ball in the FIFA championships in Africa, because the ball they had, I believe it was 1 or 2 less panels than a typical soccer ball, which changed how it reacted in air. So every sport has that aerodynamic component. So I just want to show you a little bit of the physics behind the curveball. So keep this simple, let's go, here's our direction of throw. So direction of throw. So if you want to copy that a couple times here, I'm going to cheat outrageously here and clone it. Clone. And clone. So in each case, there we go. So if we just throw it, and I'm going to call it normal. So a normal throw. What happens with the normal throw? Well, the air, I'm just going to keep it simplified for you. The air goes and travels past both sides of the ball, so the ball will travel straight. So this is if you throw a ball and it travels straight. All right. Now these two here are going to be the curveball. All right. So what happens with the curveball here? Well, you give it rotation. So people that aren't familiar with how to throw a curveball, you give your ball a rotation. And what happens then is the outside or the frictional area. Okay, so if I'm rotating it this way, the green kind of indicates my direction of friction. Okay, we have airflow going on either side. And what happens then is this region here, find my magic pen, right here we have airflow and our friction opposing each other. On this side, our airflow and our friction are in the same direction. So what happens is that when we look at the final frame here, what's happened is that there is kind of a there's kind of a low pressure region here and a high, because, do it in one more color here, and it's slowed down. Okay, that rotation on the ball causes the air to encounter a frictional force, which slows it down, whereas down here, air is sped up, and that's because the friction is kind of dragging the air and pushing it along. So because of the high velocity here, the result then is a low pressure area and a high pressure region, which means that the resulting force would be downward on my page, which means that direction of throw, you can just put original up above it. And then what happens is, I'm going to exaggerate here, final direction of flow. All right, so you have your center line. That's if it would have been thrown straight. That downward force is what's pushing that ball to curve one way or the other, so it depends on the rotation you put on the ball. Every sport has it, football, soccer, hockey, all right, and they're looking at different aspects of the aerodynamics. Baseball's a great one because of all the different pitches. Anyway, there's some real-world examples for you. Good luck with the homework. If you have any questions, I will help you in class.